We've split and sealed our data, and we have baselines to beat. There's just one problem. A model can't actually read our applicants yet. The raw table isn't model ready. So in this lesson we build the preprocessing pipeline that cleans it up, the same way, every single time. Here's one raw applicant. Look closely, and you'll spot 3 problems a model can't handle. First, a gap. This person's income is missing. Second, the scales are wildly different. A credit score in the hundreds sits right next to a rent flag that's just 0 or 1. And third, the purpose is a word, car, and a model can only multiply numbers, not text. We fix the gap first. This is called imputation, filling a missing value with a sensible stand-in. For a number like income, the usual choice is the average. We compute the mean income from the training applicants, about 55,000, and drop it into the empty cell. The gap is gone. Notice, that average comes from the training data only. Hold that thought. It matters a lot later. Now the scales. Let's line up the raw feature sizes side by side. Credit score averages around 669. Income around 55. And the rent flag is just 0 or 1. Credit score towers over everything. To a model that measures distance or follows a gradient, that giant column drowns out all the others, not because it matters more, but simply because its numbers are bigger. Remember how nearest neighbors fell apart on an unscaled feature? This is that problem. The fix is standardization. For each column, we subtract its mean and divide by its standard deviation, the z-score. That recenters every feature to a mean of 0 and a spread of 1. Our applicant's credit score of 694 becomes just plus 0.35, a little above average. Now every feature speaks the same language, and no column wins just for being bigger. Last problem. The word. The loan purpose is one of 4 categories: car, education, business, or furniture. We can't number them 1, 2, 3, 4. That would falsely tell the model business is somehow more than education. Instead we want hot encode, 1 new column per category, and we switch on the single column that applies. Car becomes 1, 0, 0, 0. With 7 numeric features plus these 4, our clean design matrix is 500 rows by 11 columns, all numbers. Here's the key idea. We don't do these steps by hand each time. We chain them into one object: impute, then scale, then encode. It has 2 jobs. Fit, where it learns the pieces it needs from the training data, the mean to impute, the mean and standard deviation to scale, the list of categories to encode. And transform, where it applies those learned pieces to any applicant. Fit once on training. Then transform anything, the test set, or a brand new applicant tomorrow, exactly the same way. Now the trap that ruins careless projects: data leakage. When the pipeline fits, when it computes that mean and standard deviation, which row should it look at? It's tempting to just use all the data, but watch what that quietly does. Take the credit score mean. Computed over all 500 applicants, it's 69.1. Computed over the training set only, it's 671.3. Different numbers. Now scale 1 test applicant, credit score 694. Using the all data mean, it becomes 0.347. Using the honest, train-only mean, 0.321. See the problem? When we used all the data, that test applicant's own score helped compute the very mean that scales it. The test set peaked at itself. That's leakage. Small here, sometimes huge, and always dishonest. The fix is a firm rule. Fit the pipeline on the training data only. Learn the mean, the standard deviation, and the categories from training. Freeze them. Then apply those frozen numbers to the test set and to every future applicant, reusing the training statistics, never recomputing on new data. That's exactly why our scaling function takes the mean and standard deviation as arguments, fit them once on train, then pass them in everywhere else. The test set stays a genuine unknown. That's the preprocessing pipeline. Impute the gaps, scale every feature to a common footing, and hot encode the categories, bundled into one reusable object. Fit it on the training data only, so no test information leaks in, then transform everything the same way. Our data is finally model ready. Next, the moment we've been building toward, a fair bake-off where every candidate model competes on the same footing.